Sorry, singers. I'm a little late. So we're talking about if I have population A and I take samples from population A, they'll be normal if my sample size is greater than 30. The mean of those sample means from population A would be the mean of population A. And the standard deviation would be the standard deviation for population A divided by the square root of the sample size. All right, now, what if at the same time we do the same thing from population B? So we're going to take a sample from population B, and we're all going to measure a different mean from a different sample from population B. When are these going to be normal? Same idea, right? All right, so if NB is greater than or equal to 30, we'd be in good shape for that normality for sample B, yeah? And the mean of these is going to be the mean of whatever population B is. And the standard deviation of these is going to be very, very similar. Oh, hold on. I screwed this up. The standard deviation of the X bars from sample B would be the standard deviation of B over the square root of N sub B. And we're starting to get this really icky looking thing that's got so much going on. But really, those A's and B's are just saying the same thing we were talking about yesterday, one for when I'm drawing from population A and one from when I'm drawing from population B. Okay? So if I want to compare the samples from two different populations, I want to think about the distribution where this one point in this distribution, like this point right here, is a difference from the sample I took from A and the sample I took from B. Okay, so it's like, oh, I went ahead, I decided to use you guys as a sample from period 8. And I want to know, does period 8 do better on a test than, say, period 2? So I'm going to use you guys as a sample, take your mean, compare that to the mean of the sample from the morning class, and we would subtract our two means and call it a day. Yeah? And our actual metric would not be your mean and their mean. It would be the difference between the two. Okay? So we're thinking about this like difference between two means. If these were both normal, are you guys with me that the population would be normal, or that the differences would be normal? Okay, so if what I'm doing is comparing two means, they're going to be normal if that normal rule for both samples works. We're just going to check those normal rules for both samples. Okay? What's the center of this going to be? Mu A minus mu B. Now, for the standard deviation, you guys don't need to write this initial part down because I'd much rather you understand it than focus on getting it written. Okay? The standard deviation of X bar A minus X bar B, we would have to do that kind of funky Pythagorean thing where we would take the first standard deviation, would be sigma of A over the square root of NA. And then we would square that. The standard deviation of the first one squared plus the standard deviation of the second one squared. But as we look at that, do you guys see like when I square both of those that just this one becomes the first, like I get rid of that square root sign and square the top because that's going to end up canceling each other out. The squared and square root sign when I square that fraction. Okay? And likewise, when I square this one, the top of the fraction will be squared, but on the bottom, the squared and the square root cancel out. And so what happens is, on your formula sheet, you have this formula to describe the difference between the standard deviation of the difference of two means, but it's really just doing that squarey thing that we've been doing for the past month. Okay? Because we have two different groups, therefore we have two different distributions that we're subtracting. All right, so let's do an example. We're going to do this one example. And then I was going to let you guys either work on corrections or study for the midterm. Okay, so you'll have lots and lots of time to do practice problems like some of the ones that are on the midterm review on AP Classroom. Okay? All right. So let's go ahead and take a look at this real quick. I'll let you guys read this because I've read this before. So I'm already familiar with the context. All right. What are some things we might want to write down, y'all? The shape is normal. The shape of what? It's going to be I take a sample of females and the sample of males, subtract their mean, okay? And we're going to do that over and over and over. And so what starts to get really challenging is that this is like this theoretical distribution where we take a sample from each group, find their mean, subtract them, put them back. Take another sample from each group, okay? All right. Now, it will be approximately normal. Why? And I swear if you say it says it is, we're going to have a problem. Okay? Both populations are normal. If it didn't say that both populations are normal, but my sample sizes were big enough, okay, that would work. All right? What is the mean of x bar f minus x bar m? Whoever's having that much fun, we have to have a problem with it, right?
Is it 0.7?
How'd you get it?
Just the mean of...
The mean of the females minus the mean of the males. Guys, by the way, is it weird that the males are shorter than the females?
No.
Not at age 10 it isn't. Likewise, did you guys notice how much bigger the standard deviation for the males versus females? Like, that's a pretty big difference in standard deviation to scale. But have you guys ever seen 5th grade boys? They're literally all over the place. Like, some are, like, tall. Most girls have already hit their growth spurt. In fact, you guys in 5th grade, Miss Meister was the tallest in her class. Everybody else kept growing, and I did not. Because I hit my growth spurt a little bit sooner than everybody else. Yeah. Hey, what about the standard deviation here? It's more work. Thank you. Perfect. Thank God we're not afraid to do a little bit of work. We're going to do a little bit of... Is anybody shocked to see a square root?
No.
Is anybody shocked to see a plus sign?
No. That's what you always do. Yeah.
Do I have the uncertainty about what's going to happen with my sample of females?
Yeah.
Do I have uncertainty about what's going to happen with my sample of males? So I have lots of uncertainty. My uncertainty is adding, not being subtracted, because I have 2 sets of it. Okay? And then let's see. Normally we would do sigma over the square root of n and then square that, but I'm just going to do 2.7 squared over 12. And then 3.8 squared over 8. And keep in mind, the formulas for mean and standard deviation, the same. Or on your formula sheet, right? It's there. So you, like the standard, it's written like this. That's essentially what we just did, yeah. On your formula sheet. I don't know what the answer is, like 1.3, 1.4? 1.55. All right, so then if we say, well, here's the difference of our sample means. And we just said it has a mean of 0.7. We just said that it was normal. We just said that the standard deviation of our difference of means is 1.55. And the question is, what is the probability our difference is less than 0? Guys, what is the probability that x bar f minus x bar m is less than 0? All right, now, you guys, what's another way to say x bar f minus x bar m is less than 0? What does that really mean? Yeah, or I'm going to say, just because I'm going to write it this way and just move that over. The girl's height is smaller than the boy's average. The average girl's height is smaller than the average boy's height. And so the probability of that happening is 0.3. So what's the probability the girls are taller than the boys in this particular case that from our two samples? 67-ish%. Are you guys with me saying that if a researcher says the girl's height is lower than the boys, that he's not very smart? Because the probability of that happening is very, very small. That's all I got for today. The rest is... I should probably record this for everybody at home too, huh? Okay, Aquafina Bottling Factory. And I'm thinking like those 20-ounce bottles, right? Where the volumes of water in a bottle are normally distributed with a mean of 20.2 ounces and a standard deviation of 0.58 ounces. I can't believe I didn't do this with you guys yesterday. So that's like the starting kind of premise. All right, and so the first question I'm going to ask you for part A might be something along the lines of what is the 85th percentile of water volume in a bottle? And my guess is Maggie's not even paying attention, so I'm not going to worry about it.
What?
Never mind. So what would you guys do here?
Just make the normal graph with
First you would draw the graph. Okay. And let's see. Normal, I'm going to go ahead and put the mean at 20.2. The standard deviation at 0.58. The 85th percentile might be, tell me when to stop. And why'd you guys have me stop there?
It's the first 85%.
It looks like about that area is about 85%. From here, we can say inverse norm in my calculator. I would imagine it's roughly 2.8 or 20.8. But I sure would love somebody, since I'm making these up as we go.
20.8.
I tried to make it one standard. The 84th percentile is exactly one standard deviation above the mean. So I was trying to like cheat a little bit with how I did that. Because I'm a cheat. Are we doing okay so far? Does that seem like a reasonable question? All right. Then for part B, for parts B and C, let's assume a 6-pack of bottles is a random sample. So for part B, I'm going to say, if I walk down the store and if we go by one, what's the probability of getting at probability more than 4 bottles? Exceed the volume found in part A. What do you guys think? All right. Anything jumping out at you when you see that? When you see a 6-pack that 6 is a random sample, are we comfortable with looking at that and maybe saying, well, doesn't that mean that n equals 6? And we're trying to find the probability something is bigger than 4? Are we comfortable with that idea? And what is that something if I asked you to define what x is? Number of bottles, yeah? Technically, that are more full than 20.8 ounces. Is this starting to ring make us think of anything? It almost looks like x is a number of successes, yes? And if x is a number of successes, that suggests binomial. And if it is binomial, there's one other thing we need to know. Binomials have the same probability of success each time. What is the probability of success each time? I'm sorry? So the probability, it's going to equal 0.15. It's going to be the other side from that 85% because those are the ones that are bigger than that value we found in part A. Are you guys with me? Okay. And then from here, you have two options. Okay. You can either look at this and say, if I have to find the probability x is greater than 4, which outcomes in this scenario are greater than 4? 5 and 6. So if you wanted to use the binom PDF and just do x equals 5, x equals 6, and add them together, cool. If not, you could also do 1 minus the probability x is less than or equal to 4, because those are the ones that are not 5 or more. And I have no idea what this is. It's going to be really small. What'd you get, Keelan?
I got 0.0003.
I buy it. I'm making these up as we go, so.
I think I did this one wrong.
Yeah. Do you know which one I'm trying to mimic here?
I don't remember what it was about, but I remember doing one like this, and I remember instead of putting it into the binomial.
Hold on.
blah, blah,
There would be a part C to this as well.
yeah. Can I go?
Yeah. Just tell me where. Sorry.
Dr. Mason.
Sure. Yeah, that's fine. If she's teaching, don't interrupt her. Mm-hmm.
So, would you keep the 0.15 if you're doing the 1 minus?
Yes.
Okay.
Are we okay? Do we want to talk about this anymore? Are you ready for part C of this question?
Let's see.
Okay. So it turns out that these bottles are supposed to have 20 ounces in them, right? Okay. So they're concerned that if a customer goes and buys a 6-pack and the average is less than 20 ounces, that they're going to get sued. So the question is, in a 6-pack, what's the probability the average volume is less than 20 ounces? All right. Thoughts? Are we still good with n equals 6? And are we cool if I say what we want to find is the probability that x bar is less than 20? Is this okay so far? And the minute I know I'm trying to find the probability that x bar is less than 20, I start thinking through all those possible x bars. She was teaching, wasn't she?
No, I brought the wrong paper, so.
And let's see. Well, what do I know about the mean of the x bars? It's going to equal the mean of my population. So the mean is 20.2. And what about the standard deviation of my x bars? It's going to be the standard deviation. Was it 0.58 that I used? 0.58 divided by the square root of 6. And then we're going to say, well, here's 20. What's the probability I'm to the left of 20? Everybody good? I don't remember the answer. Let's say 0.2. Square root of 6 is 3. What's the answer? Speaking of very large standard deviation of heights where the girls are taller than the boys. Hey, do we have an answer yet? 0.199? Sure. Okay, now I really am done. But, so did you guys see how this is like a question from the very first unit we've talked about? A question from the unit we just did and a question from this current unit. They're big fans of doing that, especially for probability.